Here are two practice problems involving Hess's law. Hess's law basically states that if we want to compute the delta H, or the change in enthalpy of a reaction, we can break that reaction down into these subreactions and then add the corresponding delta H's, add the corresponding change in enthalpies. So the idea being, add reactions, you can add the corresponding change in enthalpies or delta H's. Let's begin with this reaction. Here's our net reaction, and here are three individual reactions. The point is, how do we get to our main reaction of which we want to calculate and compute the enthalpy for that reaction from these three reactions? So notice here we have 2 carbon, or 2 graphite, plus H2 gas going to C2H2. This is called acetylene. And in our subreactions A, B, and C, we also have graphite, C, plus oxygen going to carbon dioxide. Notice here, this is a reactant. But notice here that 2 carbon, of which we want to find their enthalpy, notice here that in our subreaction, it's only 1 carbon. So what we can do is to get these reactants to match, we can multiply this first reaction by 2. In doing so, we also multiply the delta H by 2. So let's go ahead and do that. So I multiplied reaction A by 2 to get this bottom equation. 2C graphite plus 2 oxygen goes to 2CO2. So I multiplied everything by 2. And remember, one of the rules in Hess's law, the sort of gymnastics, is we have to multiply the corresponding delta H of the reaction by 2. And doing that, I get minus 787 kilojoules per mole. By the way, just as a reminder, that delta H naught of the reaction, that naught symbol as a superscript, implies that the reaction is occurring under standard state conditions. Standard state is 25 degrees C and 1 atmosphere of pressure. And now let's look at the hydrogen gas. The hydrogen gas is in the reactant side. Here in one of my sub-reactions, I have hydrogen gas also on the reactant side. So why don't we add this reaction that we just multiplied by 2 to part B. So I have the first reaction A that I multiplied by 2, and I'm going to add that to reaction B. So this would be step 1, and this would be step 2. So when we add that to reaction B, we will add the corresponding enthalpies to the reaction. And let's see what we get when we add reaction A, which was already multiplied by 2, to the reaction B above that was given to us. Right, so we added the reactions 2C graphite plus H2. 2O2 plus 1/2 O2 is 5/2 O2, and that goes to 2CO2 plus H2O. So adding minus 787 kilojoules per mole that we got from the first reaction multiplied by 2, adding that to reaction B, which was given to us an enthalpy of minus 285.8, add them up, we get minus 172.8. So one nice thing here is that 2C graphite and the H2 gas that we see in our reactant side are in our reactant side here in the equation that we want to calculate the enthalpy for. Finally, we see here acetylene, C2H2, is in the product side in the reaction that we want to find the enthalpy for, the unknown enthalpic reaction. And C2H2 here in reaction C is in our reactant side. So what we can do is flip this reaction, and when we flip a reaction, we flip the sign, and let's do that. And the reasoning why we'll do that is, again, to get the C2H2 that is on our reactant side in reaction C to become on the product side, which is what C2H2 is on the product side here. After we've reversed this reaction, what we'll do is we'll add it to this new reaction. So we flip reaction C, we flip the sign, so it's now, instead of minus 1479.4 kilojoules per mole, it is positive. And then we'll add it to this reaction here that's highlighted, which we got from step 1 and step 2. So adding that, we'll see automatically that this 2CO2 and the H2O cancel out with the 2CO2 and H2O here from this reaction. The 5/2 O2 gas on the product side here cancel out with the 5/2 O2 gas on the reactant side here. The net reaction is now made, and the enthalpy is going to be minus 1072.8 plus 1472.4 kilojoules per mole. So our net reaction is made, and the corresponding free and standard enthalpy of formation of that reaction is 407 kilojoules per mole. It is an endothermic reaction. Let's do this problem here, our second problem. The enthalpy of this reaction is something we want to calculate. This is a little bit more difficult. How are we going to get these 5 reactions and manipulate them in such a way so that we can get the delta H of this unknown, realizing that we can just add the delta H's of individual reactions to get the delta H of the total reaction. So first thing I see here is a 2N2O4 on the product side, and I see a N2O4 on the product side here. The problem is this is only 1 mole and that is 2 moles, so I think we'll just multiply this out by 2. That's one strategy. Another thing I see here is an N2O3 gas. N2O3 gas is in the reactant side in the unknown reaction, and here N2O3 is in the product side. So already we need to do a couple of manipulations. One is, let's flip reaction 1 so that N2O3 is on the reactant side. So remember, we flip reaction 1, we will flip the sign. And another thing we can do is we can multiply reaction 3 by 2. That gives us 2N2O4, and 2N2O4 is in R. So I flipped the first reaction, so we flip the sign. I'm going to call this reaction 1A. Remember, multiply the reaction. We also multiply the delta H of the reaction, and so I get minus 114.4 kilojoules, and I'll just call this 3A. The next step, I think what I'll do is I'll get the N2O3 in the reactant side and the N2O4 on the product side, so I will just add reaction 1A and reaction 3A. So I added reaction 1A and 3A, and I got this reaction. And for lack of anything better, I'll just call this reaction 4A. Remember, we got to add up the enthalpies of the reaction. This is in standard state. That I get minus 74.6 kilojoules. Well, I'm a little bit far away from what I want because, well, I do have the N2O3 on the reactant side. I do have the 2N2O4 on the product side. But I got all of this other intervening stuff that I need to try to find a way to cancel. This reactant here, N2O5 solid, I'll put that in reactions here that we can manipulate. I see an N2O5 solid here in the reactant side. So let's just go ahead and add reaction 5. That way I can get my reactant N2O5 into the mix. And be careful. Okay, this is solid. And this is solid here in reaction 5, so we do not need to flip it. So I added reaction 4A to reaction 5 that was given. Things are getting a little bit complicated here, but remember one of the cardinal rules of Hess's law, you add reactions, you add the corresponding enthalpy. So my N2O3 plus 4NO2 plus my N2O5 solid, that has to go to NO gas plus NO2 gas plus N2O5 gas. And now I got all my reactants where I want them to be. Okay, my blue reactant, my green reactant, and my red product, and we're getting minus 20.5 kilojoules. So now I'm in a situation where I need to find a way to get rid of all these NOs and NO2s and 4NO2s because really my reaction is right here. I think what I will do is I'm going to flip reaction 2 and add it to all of the computations that I've done so far. The reason why I want to flip reaction 2 is because that N2O5 gas now becomes on the reactant side, and if we go all the way down to reaction 5A, the N2O5 here is on the product side. So let's flip reaction 2 and add it to reaction 5A. Alright, now so the problem is getting pretty complicated for my tastes, but let's cancel out the N2O5 gas, which is what I wanted to do in the first place. So that's gone. The NO here is on the product side, and the NO here is on the product side here, so that's going to be 2NO. One thing I also want to mention is that this 4NO2 that's in the reactant side can also cancel out with the NO2s on the product side. As an alternative, what we can do is we can cancel out one of the NO2s here with one of the NO2s here, and that will leave us with 3 NO2s. So I'll cancel one of the NO2s with the 4 NO2s here, giving me 3 NO2s. To be honest, I could have done it up here. I could have canceled one of the NO2s here with the 4 NO2s in the reactant side, giving us or leaving us with 3 NO2s, but I went ahead and did it here. So I just caught my attention. So we have 3 NO2s here. This is on the reactant side. This NO2 is on the product side. So I can do another cancellation. One of the product NO2s will cancel out with one of the reactant NO2s as I add them, leaving me with 2 NO2s left on the reactant side. So let's clean up a little bit of this mess. I'm going to have N2O3 gas plus 2NO2 plus N2O5 solid goes to NO plus another NO, giving 2 NOs plus O2 gas plus 2 N2O4 gas. Let's add up the corresponding enthalpies. So after clearing up all of this, we added the enthalpies and got minus 133 kilojoules. I'm going to call this, for lack of anything else, 6A. And we still got our reaction here. And now let's go back and see what we can do to get rid of the NO2s, the NOs, and the O2s. And I believe that will have to be reaction 4 because that's the only reaction that we have not used up. So I have a little bit of a messy situation here, but I still have all the reactants and products in the right place. And now I need to find the reaction that will get rid of the 2NO, the O2, and the 2 NO2s. And I think that would be reaction 4. So let's go back up to reaction 4. And reaction 4, here we have the 2 NO2s in the product side. In reaction 6A, the one we just made, here it is in the reactant side. 2NO and O2 are on the product side. Go back to reaction 4, 2NO and O2 on the reactant side. So I can just straight up add reaction 4 to this new 6A that I just made, and that should give me my net reaction upon which I want to calculate the enthalpy of the reaction 4. So this step is to add reaction 4 to 6A. So let's go ahead and do that, add our enthalpies, and we should get our final answer. So let's add these two reactions. The 2NO gas on the reactant side here will cancel with the 2NO gas on the product side there. The 2NO2 gas on the product side here will cancel with the 2NO2 gas on the reactant side there. The O2 gas on the reactant side on this reaction, reaction 4, will cancel out with the O2 gas here, and I'm left with NO3 gas plus NO2O5 solid goes to my product of N2O4 gas. So adding up reaction 4 to reaction 6A, I cancel out all the intervening substances. I get the final reaction, which is the reaction that is unknown in terms of enthalpy. I add the two enthalpies that I get after my manipulations and gymnastics. Minus 133 plus a minus 114.2 gives me an enthalpy for this reaction of minus 247.2 kilojoules. So let's go back up. The enthalpy for this reaction that we calculated is minus 247.2 kilojoules. So a little bit of an involved problem involving Hess's law, a lot of manipulation and quote-unquote gymnastics, but eventually we were able to solve this problem and getting our enthalpy for this unknown.